An induced EMF is short for an induced electromagnetic force. So if you take a coil of wires and you push a magnet into the coil of wires, if you push the magnet such that the North Pole moves into the coil of wires, then the galvanometer that is connected to the circuit will register a slight deflection, meaning the pointer will move to one side. So the galvanometer, as you may recall, is a device that can measure tiny amounts of current, and it can also tell you which direction the current is flowing based on the pointer. So this indicates the presence of current flowing in the circuit, or what we call an EMF, right? It must have been induced when the magnet was moved into the coil. Remember, induced means that it causes something to happen without actual physical touch. So without the magnet actually touching the wires, it causes a current to flow through the wires. So the force of magnetism, as it is being pushed into the wires, then pushes on the electrons and causes them to flow. In other words, a current. Something to note is that when the magnet is stationary inside the coil, there will be no deflection in the galvanometer. In other words, no current is flowing. There is no induced current. When we take the North Pole and move it out of the coil in the opposite direction, the galvanometer will show a deflection the opposite way. What we can deduce is that the current is induced in the opposite direction. In conclusion, an electromotive force, and hence a current, is induced whenever there is a change in magnetic field inside a coil. This experiment shows that the direction of the induced EMF opposes the change producing it. So in other words, if the North Pole goes to the left into the coil, then the current will be acting to the right, such that it is the motion of the magnet that is opposed. And on the other hand, if you take the North Pole and move it out of the coil, in other words, you move the North Pole to the right, then the magnetic induced current will be to the left. This then brings us to Lenz's law, which states that the direction of the induced EMF is in a direction that opposes the change that gives rise to it.
So why don't we drop something through it and just make sure it's empty, right? Okay, this is not a magnet, so this isn't a magnet, but let's see what happens when we drop it through. That was a dull experiment, wasn't it?
Yeah.
Okay, so what's gonna happen if we drop this magnet down the pipe? It's gonna pull through. Let's do it. 3, 2, 1.
That was weird.
That's well cool.
Took longer.
What's slowing the magnet down?
Does it like...
Kind of tilts. I think it's...
So as the magnet is falling through the pipe, it's creating a changing magnetic field that generates little electric currents, so-called eddy currents, in the pipe, and they create an opposing magnetic force on the magnet, slowing it down. So there's actually energy being converted from gravitational potential energy into electrical energy and eventually to heat.
What are some things that can affect the size of the induced current? Well, first, the speed at which the magnet is moving. So if you move the magnet faster, then you're going to get a larger current. If you move the magnet slower, you're going to get a smaller induced current. If you use a stronger magnet, then you're going to have a greater induced EMF. A weaker magnet, a smaller induced EMF. If you use more turns of the coil, then you're going to have a greater induced EMF. It is also key to note that the greater the turns, the harder it is to actually push in the magnet into the coil, because there is a more resistive force since there is more coil, in accordance with Lenz's law. Remember that the induced EMF always acts to oppose the change which is bringing it about. So when you are trying to push the magnet into the coil, then the current that is produced opposes that action. So if there is more coil where there will be more current, then there will be a greater resistive force trying to stop the magnet from going into the coil. So this leads us to Fleming's right-hand rule. Instead of taking electricity and magnetism to produce a force, now we're doing sort of the opposite. We're taking a force and magnetism to produce electricity. So using Fleming's right-hand rule, as you see here, your thumb is the direction of the force or the motion. Then your index finger is the direction of the magnetic field. So you will line up those two first, and then, dependent on those two, your middle finger will give you the direction of the induced current. Let's keep in mind that the AC generator is different from the motor. Motors, they convert electrical energy to mechanical energy. Meanwhile, generators do the opposite. They convert mechanical energy to electrical energy. So a generator consists of a fixed coil between the poles of two permanent magnets. When the coil is rotated, the magnetic field through it changes, and as we have previously learned, according to Faraday's law, an induced EMF will be present. So the current then flows through the two slip rings, X and Y, as shown in the diagram, which are in sliding contact with the fixed carbon brushes P and Q. Let's now look at the voltage output of an AC generator. When the output of a generator is connected to a cathode ray oscilloscope, the graph of the induced electromotive force plotted against time is shown in the diagram to the right. When the coil is horizontal, the rate at which it is cutting the magnetic lines is the highest. Hence, the induced electromotive force is maximum, as shown in positions B and D. When the coil is vertical, the rate at which the coil is cutting the magnetic lines is the lowest. Hence, the induced electromotive force is minimum, 0, as shown in positions A, C, and A'. You may recognize this graph here as the simple graph that we have learned about before of alternating current. Why is there a maximum and a minimum current? Well, it's like this. As we had previously learned before, there are many factors that will affect the size of the induced EMF. One of them that we'll be looking at is the angle. It's like when you're opening a door. The angle at which you pull on the door makes a difference. You would normally put your hand on the handle and you pull perpendicular to the door. That way you get the door to open easily. If you were to instead push on the lock of the door, as we see here, parallel to the door, would the door move? No, because the angle makes a difference. The angle here that is key is 90 degrees. That angle of 90 degrees makes you maximize the force. So with that same idea, when the angle of motion is 90 degrees, then the induced current will be the greatest. Keep in mind though, it's the angle of the motion, not the angle of the coil, not the coil's position that should be 90 degrees. When the coil is horizontal, its position is parallel to the magnetic field, but its motion will be perpendicular to the magnetic field. Perpendicular meaning 90 degrees. That special angle of 90 degrees is where you have the most induced current. So as we see here, when the coil is vertical, its motion will be parallel to the magnetic field. So when it is parallel, the angle between the motion and the magnetic field is 0. And so the sign of 0 is 0. But when the coil is horizontal, its motion will be vertical. And then the sign of 90 degrees, because it is now perpendicular to the magnetic field, right? The motion is perpendicular to the magnetic field. The sign of 90 degrees will be 1. So the maximum induced current is seen when the coil is horizontal, and the minimum current, 0, is when the coil is vertical. But let's distinguish again between the two. When the coil position is horizontal, it is parallel to the magnetic field, but the motion will be vertical, which is perpendicular to the magnetic field, and vice versa. Next, let's look at 4 ways that we can increase the induced EMF in an AC generator. In other words, how can we get more current from a generator? Number 1, use stronger permanent magnets. 2, increase the number of turns of the coil. 3, increase the frequency of rotation of the coil. And 4, decrease the distance between the permanent magnets and the coil. So if you use stronger magnets, you're going to get a greater current. If you have more wire turned around on the coil in the generator, you're going to get more current. If you spin it faster, right, increase the frequency of rotation, in other words, spin it faster, you're going to get more current. If you decrease the distance, what does that mean? It means bring the magnets closer to the coil. If you bring the magnets closer to the coil, you're going to get a greater induced EMF.